Hi everyone, I'm Dan Fullerton, and today I'd like to talk to you about rotational dynamics and solving some problems involving rotation. So to begin with, let's talk about our objectives. We're going to determine the angular acceleration of an object when an external torque or force is applied, determine the radial and tangential acceleration of a point on a rigid object, analyze problems involving strings and massive pulleys, analyze problems involving objects that roll with and without slipping, and applying conservation of energy to objects that are moving both translationally and rotationally. So with that, let's dive in. Conservation of energy we've talked about before, especially conservation of mechanical energy has been pretty useful to us so far. Well, now we're just adding a slightly different piece. We have our traditional conservation of translational or kinetic energy. Translational is 1/2 mass times the velocity squared, and that's the velocity of the center of mass. Well, we also have to take into account that objects that are rotating or spinning also have kinetic energy. The energy from all those little pieces that are rotating, they also have a velocity. So the rotational kinetic energy is 1/2 times the moment of inertia times the square of the angular velocity. So the total kinetic energy at any point in time is the translational plus the rotational components of kinetic energy. That's going to be pretty useful here in just a moment. If we have a problem where we want to find the speed of a disk of radius r, which starts at rest and rolls down an incline of height h, how are we going to do that? Well, as we begin this, one of the things that I can tell already is probably going to be useful to know is that the moment of inertia of our disk is going to be 1/2 mr squared. You can look it up, probably should have that memorized by now, or you can derive it if you'd like, going back to our moment of inertia presentation. But I bet that's going to come in useful. Now, the way I would look at solving something like this is realizing that we have some amount of energy at the top, and we must have that same amount of energy at the bottom, assuming that we're not losing anything to non-conservative forces here. So I would say that the kinetic energy at the top plus the potential energy at the top, initial, must equal the final kinetic energy plus the final potential energy. Now, realizing here up at the top when it's at rest, its kinetic energy is 0, so our initial kinetic energy is 0. And down here at the bottom, let's call that our 0 of potential energy. So final potential energy equals 0. We can now say that the initial potential energy equals the final kinetic energy. All right, let's go a little bit further. The initial potential energy is gravitational potential energy, mgh. So capital M, the mass of our disk, times the acceleration due to gravity on the surface of the Earth, little g, times the height, h, must equal the final kinetic energy. But now we have to realize our final kinetic energy has translational and rotational components. So that's going to be 1/2 times the mass times the translational component, the square of the velocity of the center of mass, plus 1/2 I omega squared. All right, we also know now that I, our moment of inertia, is 1/2 mr squared. So I can rewrite this as mgh equals 1/2 mv squared, and I'm just going to leave off the center of mass. The velocity v right there, we're going to refer to that just as the velocity of the center of mass, plus 1/2 times I, 1/2 mr squared, omega squared. All right, getting a little closer here. Notice I have an m here, here, and here. I can divide everything by m and simplify this a little bit. We've got the m's taken out there. So when I rewrite this now, I could write this as gh equal to v squared over 2 plus, over here I've got 1/4 r squared omega squared. Okay, getting closer. Now, notice I have a v and an omega in the same equation. Well, remember we've got a relationship that ties those two together. V is equal to omega r. Oh, wait, there's r and omega. Omega r, and that's squared. So I could rewrite this as GH is equal to v squared over 2 plus v squared over 4. Well, that's 2 fourths plus 1 fourth is going to be 3 fourths. So that's GH equals 3 fourths v squared. And if I'm solving for the speed, well, let's get v all by itself with a little bit of algebra. V squared is going to be equal to 4/3 GH. Therefore, it's pretty easy to see if I take the square root of both sides that v is going to be equal to the square root of 4/3 GH. Okay, application of conservation of energy, but now we're taking into account the rotational component as well. All right, let's move on here. When we talk about rotational dynamics, we've already talked about Newton's second law for translational motion. The net force is equal to the mass times the acceleration, and force and acceleration there are vectors. The same token, Newton's second law for rotation says the net torque must equal I alpha, the moment of inertia times the angular acceleration. And we can also use this to help us solve a variety of problems as well. Let's keep going here and see what else we can learn. We have strings, but now our pulley isn't an ideal pulley. Our pulley has a mass. 2 blocks are connected by a light string, so we can assume the string is massless in this problem, over a pulley of mass m sub p and radius capital R. So the radius of our pulley is r. Find the acceleration of m2 if m1 sits on a frictionless surface. And one of the first things I'm going to do here is realize that I'm going to call that our positive direction, just setting a standard so that we've got everything lined up as far as our signs go. All right, problem like this, bunch of ways to solve it, but I'm always a big fan of starting with free body diagrams and then going to Newton's laws. Usually a good place to start. So let's start by looking over here at mass 1, m1. If I were to draw a free body diagram for that, there's mass 1, there's its center of mass, we have its weight, m1g, down, we have the normal force, up, and we have T1, tension 1, pulling to the right. And notice in this case that tension 1 and tension 2 are going to be different. If they were the same, the pulley wouldn't rotate. So now that we're talking about real pulleys instead of ideal pulleys, the tension everywhere in the string is not necessarily the same. From here, I could use Newton's second law. The net force in the x direction, well, all we have is T1, and that's going to be equal to m1a, the acceleration. Let's try the same thing now, but let's do it now for m2. For m2, there's our center of mass. We have its weight, m2g, down, and we have T2 pointing up. Now the net force in the y direction, we're going to have m2g, we'll call that positive because we called down over here positive, m2g minus T2 equals m2a. And while I'm here, let's just solve that for T2. I can rearrange this to say that T2 then must equal m2g minus m2a. And now let's take a look at our pulley over here. As we look at our pulley, from its center of mass, we have the weight of the pulley, MP, mass of the pulley, times G. We have the force of the pivot on that, FP, and we also have the 2 tensions. We have T2 down, and we have T1 to the left. And these both are operating at a distance r from the point of rotation. So here, I'm going to take a look at the net torque and say that the net torque must be, well, T2r, pointing in my positive direction, minus T1r, pointing in the opposite direction, must equal I alpha, the moment of inertia of the pulley. All right, the other thing I'm going to point out here is the moment of inertia of the pulley, if we model this as a disk, its moment of inertia, again, is going to be 1/2 mp r squared. Okay, so I've got a couple equations. I've got an equation for T1, for T2, and an equation for moment of inertia in alpha. What I really need to get to here is the acceleration. So what I'm going to do is I'm going to start with this net torque equation here, and I'm going to substitute in T1 for T1 over here, and T2 for T2 right there. So what I'm going to come up with here is an equation that says the net torque is going to be equal to, well, I've got T2R, where T2 is m2g minus m2a, there's T2, times R, minus, well, now T1, we already said, well, that's m1a times R, and that must be equal to I, well, I is 1/2 mp r squared times alpha. And if you remember, alpha is a over r. Translating this from rotational acceleration, angular acceleration, to translational acceleration. So I'm going to replace alpha with a over r. Just trying to get my equation in terms of variables I can solve for. Because now I know m2, I know g, I'm solving for a, I know r, I know m1, I'm still solving for a, I know the mass of the pulley, I know r. Now I've really got an equation just in terms of one variable. One equation, one unknown, I should be able to solve for a. So let's go a little bit further here and see what we can come up with. This implies then, well, I've got an r, and an r. I can make divide all those by r to make a ratio of 1 or cancel some of those out. That squared goes away. And over here on the right, I've got r over r. That'll go away. So I'm left with m2g minus m2a minus m1a equals mp over 2a. Well, if I'm solving for a, it'd probably be helpful to get all those a's on the same side. So let's see what we can do toward that end. If I add m2a and m1a to both sides, my left-hand side remains m2g must equal m1a plus m2a plus mp over 2a. And I can pull the a out of the right-hand side to say that m2g must equal a times m1 plus m2 plus mp over 2. Now to get a by itself, if I divide both sides by this quantity, m1 plus m2 plus mp over 2, I come up with an acceleration of m2g over m1 plus m2 plus mp over 2. Okay, using net torque equation equals I alpha plus Newton's second law, F net equals ma, all in the same equation, or all in the same problem, excuse me. So let's go a little bit further and see what else we can figure out here. If we talk about an object that rolls without slipping, now we've got a disk that's going to roll down this incline that has some angle theta, and we want to find the force of friction on the disk. Okay, let's take a look at how we might do something like this. First thing I'm going to do, probably draw a free body diagram. So there's our x-axis, there's our y. We'll call down the ramp the positive x direction, and we have our disk centered on our free body diagram. Forces acting on it, well, we must have its weight, mg. We must have the normal force, N, acting out of the plane of the ramp, and the force of friction. And the force of friction is going to act at the point of contact. So our force of friction here must be that way. Now notice here in our free body diagram, this mg doesn't line up with an axis. It's awfully helpful if we can take that weight and break it up into components parallel with the axes. So I'm going to draw a pseudo free body diagram right beside it here. And especially important on the AP exam is to draw a separate diagram. Over here is your official free body diagram. The diagram on the right is probably going to be more helpful for problem solving though. So there's our disk. We still have the normal force. We still have our force of friction. Those are already parallel with axes. But this mg, breaking it up into components, I'm going to have a component parallel with the x-axis. That's going to be mg sine theta. And a component perpendicular to the axis, mg cos theta, or parallel to the y-axis. All right, now as I start to get into the problem-solving aspect here, typically helpful to start with Newton's second law. So the net force in the x direction, if I take a look at this, net force in the x direction, I have mg sine theta minus the force of friction, and all of that has to equal my mass times the acceleration down the ramp. All right, let's do the same thing in the y direction. Net force in the y direction, I've got normal force minus mg cos theta must equal mass times acceleration in the y direction. But note, common sense tells us our disk isn't going to go accelerating off of the ramp or into the ramp. So we know the acceleration in the y direction here is 0. So if that's equal to 0, then we can say the normal force must be equal to mg cos theta. All right, that's pretty useful. Let's also go now and take a look at the net torque. If I take a look at the net torque on the system, net torque, the only thing we have here for torque is F operating at a lever arm of R. So we have Fr equal to I alpha. Now again, we've got a disk. So if you recall, the moment of inertia of a disk rotating around its center of mass is going to be 1/2 mr squared. So as I come back here, I'm going to replace my moment of inertia I with 1/2 mr squared to say that Fr equals 1/2 mr squared alpha. And right away, we see that we have an r that we can divide out of both sides. 1r and the squared will go away there. And we also should know that a is equal to r alpha. So r alpha I can replace with linear acceleration a. So what I get is F equals 1/2 ma, or ma over 2. So we know friction is ma over 2. But we're trying to solve for the force of friction, and that really doesn't tell us a whole lot yet. But what I can do is I can look back up here at my previous equations, and I can see that ma is equal to mg sine theta minus F. Little bit of substitution here, and I could write that F is equal to, ma is just going to be mg sine theta minus F divided by 2. Multiply both sides by 2 to say that 2F equals mg sine theta minus F. And if I add F to both sides, this becomes 2F plus F, or 3F. So 3F equals mg sine theta, or to get F by itself, divide both sides by 3, and my force of friction is mg sine theta divided by 3. Force of friction, again using Newton's second law for translational motion and for rotational motion. All right, so that's rolling without slipping. Let's try one more problem, this time some rolling with slipping. And this is going to be a bit more in-depth, so take your time on this one. There's a lot to it. So let's see where we go here. A bowling ball of mass m and radius r skids horizontally down the alley with an initial velocity of v0. And when I say that it skids, let's assume that as it begins, it has no rotational motion whatsoever. It's pure translational motion. Of course, as it slows down, as friction starts to take a hold, eventually it'll start rolling. Let's find the distance the ball skids before it starts rolling, given some coefficient of kinetic friction. All right, where do we start here? Well, a bowling ball is a solid sphere. You could look it up, you could derive it, but the moment of inertia around the center of mass for a solid sphere is going to be 2/5 mr squared. Helpful to know as we get started. Now let's take a look. Here's our bowling ball. Forces on it as it travels down the alley. We've got its weight, mg. We have the normal force, N. And at the point of contact, we have some frictional force, and this is kinetic friction, F sub k. So once again, I'm going to look at Newton's second law as a good starting point. The net force in the x direction is minus the force of kinetic friction, and that has to equal mass times our acceleration. Well, in the y direction, it's pretty easy to see that it's not going to accelerate, so the normal force must balance the weight. So in the y direction, we could also say that the normal force equals mg. And if you recall, the force of friction is just mu times n, so the force of kinetic friction must be mu k times the normal force, or mu k mg, replacing our normal force with mg. So that's a good place to start. From here, I'm going to go back to our Newton's first law equation. Net force in the x is minus Fk equals ma. But now that I know force of friction is mu k mg, I'm going to replace force of kinetic friction with mu k mg. So minus mu k mg must be equal to ma. Or, solving for a, realizing our masses are going to make a ratio of 1, I can divide both sides by m. A is going to be equal to minus mu k g, our linear acceleration. Well, now let's go back to our kinematic equations. Translationally, our velocity is going to be equal to the initial velocity, v0, plus at. Well, we also know a is minus mu kg now, so I could rewrite this as v is equal to v naught minus mu k g, our acceleration, times time. Okay, now let's take a different path. We've got our linear velocity. Let's see what we can do with the torque in this problem now. So I'm going to come back to the net torque equation. Our net torque here is going to be equal to the force of friction, Fk, times the radius, r. So force of kinetic friction times r must equal I alpha. All right, but we know some other things already. We know the force of kinetic friction, we figured it out up here, is mu k mg. So because Fk equals mu k mg, I also know here that I, our moment of inertia, for a solid sphere is 2/5 mr squared. I could write now that mu k mg r equals 2/5 mr squared alpha. Already there are a couple simplifications I can make. I've got a mass on both sides. I've got a r on both sides. So I could rewrite this as mu k times g equals 2/5 r alpha. All right, but we also know here, well, at this point, why don't we solve for alpha? That should be pretty easy. Alpha then is going to be equal to 5 mu k g over 2r. Now let's go to our kinematics for rotational motion, just like we did when we were doing it with translational motion up here, to say that the angular velocity is equal to the initial angular velocity plus alpha t. And in our case, because we said initially it's not going to have any rotational aspects, our initial angular velocity, omega 0, is equal to 0. So omega is just going to be equal to alpha t, or 5 mu k g over 2r times t. So if we look here, we've got our linear or translational velocity, and we have our angular velocity. Wouldn't it be nice if we could somehow relate these two to solve for the time? Because once we know what the time is going to be, where those two are going to be equal, well, now we know when it's going to start rolling. So the way I would do that is I would use the translation from translational velocity to angular velocity. We can use the equation v equals r omega to do that. I'm going to give us a little bit more room over here in order to do that. If v equals r omega, let's come down here and start with that. If v equals r omega, I'm going to replace my left-hand side v with what I had up here, v equals v naught minus mu k gt. So v equals v naught minus mu k gt, and that has to be equal to our r times our angular velocity, which we just solved, 5 mu kg over 2rt. So 5 mu kg over 2r times t. All right, if we look, v naught mu k g, t is our variable, r we know 5 mu k g over 2r, all constants, t. We've got one equation, one unknown. We should be able to solve for t. Just a little bit of algebra. So I would rewrite this then to say that v0 equals, let's add and get mu k gt to both sides to get all the t's together. So that's going to be mu k gt plus, well, over here we've got r over r. That's going to make a ratio of 1. So we're going to have 5 mu k g over 2 t. So we've got mu k gt plus 5 halves mu k gt. That's going to be 7 halves mu k gt. Okay. From there, we can solve that for t. T equals, that's going to be 2v0 over 7 mu k times g. So now we know the time at which those two are going to be equal, when the ball starts to rotate. Okay, once we know the time, we should be able to go back to our translational kinematics to figure out how far it's gone. The way I would do that is I would come over and I would start with, well, let's give ourselves some more room again, our kinematic equation, delta x equals x0 plus v initial times t plus 1/2 a t squared. And we know x initial is 0. That's going to be the 0 point of our bowling alley. We know v naught, that's a given. T we just solved for, and a we got very early in the problem. We said when we started that a up here is minus mu kg. So this should become an exercise in algebra pretty quickly. So that's going to be equal to v0 times rt, 2v0 over 7 mu kg plus 1/2 times our a. Again, we said that our a was minus mu kg times t squared, which is going to be 2v0 over 7 mu kg squared. All right, looks like we've got some algebra to do, but we know how to do algebra. Should be okay here. I would take my next step now and say that over here, 2v0 squared, 2v0 squared over 7 mu kg minus mu k g over 2 times, well, now we have 4v0 squared over 7 times 7, 49 mu k squared g squared. And I've got some simplifications I can make. Got a mu k up here, that'll get rid of the square down there. I've got a g here, that'll get rid of the square down there. And I've got 4 over 2, well, that's just going to be 2 up there. So I would say then that, and that's still equal to delta x, which is going to be 2 v naught squared over 7 mu kg minus, well, we have 2 v naught squared over 49 mu kg. All right, in order to combine these, it'd be helpful if they had the same denominator. So if I multiply the top and bottom of this expression by 7, I'm really multiplying by 1. So I can rewrite that as delta x equals 14 v0 squared over 49 mu kg minus 2 v0 squared over 49 mu kg. So 14 over 49 minus 2 over 49, I'm going to get a delta x of 14 minus 2. That's going to be 12 v0 squared over 49 mu kg. There's the distance our bowling ball is going to travel before it starts to rotate. Again, the key here, Newton's second law, translationally and rotationally, and we had to use the key point that at the point where it's going to rotate, the velocity equals r omega. It's no longer slipping. This equation only holds when an object is rolling without slipping. So the point where that holds true is where we solved for the time and then used that time in our kinematic equation for distance. All right. Hopefully this gets you started on dynamics problems involving rotation. We talked about conservation of energy. We talked about Newton's second law for translational and rotational motion. We used torque. We used moment of inertia. We're really pulling all of this stuff together to make one coherent picture. If you need more help or looking for more information, check out aplusphysics.com. Thanks and make it a great day.